In this video, we're going to find the volume of a solid whose cross-sections are described to us. Find the volume of the solid whose cross-sections are perpendicular to the x-axis, running in between the planes at x equals -1 and x equals 1. The cross-sections themselves are equilateral triangles that run from the x-axis to the semicircle y equals the square root of 1 minus x squared. So I've already graphed the semicircle, and what I am told in a few parts there is that the cross-sections are perpendicular to the x-axis, starting at -1 and ending at +1. So I can imagine those planes that the solid runs between here and here. And then I'm told the cross-sections themselves are equilateral triangles. So I have several equilateral triangles here, or triangles I'm willing to pretend are equilateral. The little green ones aren't particularly good, but we'll just pretend those are equilateral triangles. We're going to pretend that all of the sides are the same length. And so this is a cross-section of the solid at that particular x value. And that's what we're really being told about the cross-sections, is that at each x, the cross-sections are little equilateral triangles that are perpendicular to the x-axis. So I get some solid that's kind of generated using equilateral triangles whose bases run between the semicircle and the x-axis. And so I start getting this picture in my head of all these different little triangles along the way coming straight up out of the board and generating the solid. Now I only cut 5 little triangles out here, so I'm not getting a clear picture of the surface of the solid, but it will still be enough information to find its volume. Plus, I'll be able to show you a different representation of it here just in a minute. But I imagine always having a triangle for every value of x, and then I'd have a three-dimensional solid that looks something like that. So we see a ridge forming at the top, and a wall that kind of would be straight, even though it gets longer as you go out, and then a curved side on that side. And so what I really have is a solid that's going to end up looking something like this. Now, the cross-sections on this particular block of wood, they are triangles. Unfortunately, they're not equilateral triangles, so we'd have to use our imaginations just a little bit. In the solid we're describing here, this side would need to be a little more steeply generated to form that equilateral triangle. But we can see the general idea of the shape. Right, it would fit in my circle. The triangles run from the x-axis to the circle, generating this kind of wedge shape. And so this is the general idea of what we're trying to find the volume of. All right, well, we know that to find the volume of a solid based upon its cross-sections, we need to integrate an area function. Because if I multiply an area by a little height, I get a volume. So here the idea is each little cross-section is a triangle, and I multiply by a dx, and all of a sudden I'm finding the volume of a triangular prism, as if I took one of these and I just gave it a little thickness. Well, in truth, this does have just a little bit of thickness, right? A very small triangle. So a of x times d of x representing the volume of one of these. So now we just need to figure out how to talk about the area of one of these little equilateral triangles. So that's my next goal, is to find an area function. Well, my a of x here will be the area of this triangle, and we know how to do that. That's 1/2 times the base times the height. And so I just need to figure out what the base and what the height are. Now, each one of my triangles runs from the x-axis to the semicircle. And so that length right there is literally the function value itself. So the base is the square root of 1 minus x squared. If you're at this x, that edge runs from the x-axis to the function, and so that y value gives me the length of the base. Well, it's an equilateral triangle, so to find the height, I can think about this being a 60-degree angle or a pi-thirds radian angle. And I'm looking for this height, so I'm going to say the sine of pi over 3 is equal to, well, the opposite side over the hypotenuse. And I have this side labeled, but it's an equilateral triangle, so this side has to have the same length. So the hypotenuse is the square root of 1 minus x squared as well. So the sine of pi thirds is equal to h over the square root of 1 minus x squared. And fortunately, we know the sine of pi thirds is the square root of 3 over 2. So we can get h by itself, and now I know the base and the height. Let's see. 1/2 times the base times the height. Well, the height would be root 3 over 2 times the bottom here. So the square root of 1 minus x squared. 1/2 times root 3 over 2 would be root 3 over 4. Root 1 minus x squared times the square root of 1 minus x squared is just 1 minus x squared. And we found our area function. The area of any one of these little equilateral triangles is the square root of 3 over 4 times 1 minus x squared. That's our area function that we need to integrate. So we'll be integrating from -1 to 1, root 3/4 1 minus x squared dx. And there's nothing particularly challenging about that integral, so I'm just going to move it to another board and we'll evaluate it. But I think I want to do something a little sneaky. I'm always interested in making my work as easy as possible, and if I look at our region, it's symmetric on either side. So this half of the volume is equal to this half of the volume. If I think about what we saw when we drew it out here is, for every triangle over here, there's a matching triangle over here. So what I'm going to do is I'm going to find half the volume from 0 to 1, and then just double it. So what I'm looking for is twice the integral of root 3 over 4 times 1 minus x squared dx evaluated just from 0 to 1, right? Half of the region, literally saying, hey, I'm going to find half that volume and multiply it by 2. So let's see, I can factor the root 3 over 4 out front, and my fraction would reduce to a root 3 over 2. Now I just have the integral from 0 to 1 of 1 minus x squared dx, root 3 over 2. And now we just need to find an antiderivative, x minus 1/3 x cubed evaluated from 0 to 1. 1 minus 1/3. Plugging in the zeros easy. That was the advantage of deciding to look at half of the volume and double it. Now we have to be careful. If we're going to do this trick where we double half the volume, we have to make sure there actually is symmetry in the region that we're talking about. Oh, let's see. 1 minus 1/3 is 2/3, so I have root 3 over 2 times 2/3, which is just the square root of 3 over 3. And there is the volume we were looking for of a region that looks something like that, but actually built from equilateral triangles. That's it for now.